Hello everyone, let's start our discussion on string matching data structures and algorithm. Today we are going to talk about Trie Data Structure, which is used for string matching and storing strings. Okay, so let's start with a few examples which you all are familiar with. So you know about autocomplete. So whenever you are searching in, say, in Google or any other search engine, once you start typing, actually it starts showing you, after you type a few characters, it starts showing you some suggestions, like this is called autocomplete, right? So for example, this is a search I was doing uh, minutes ago, and after that what I was seeing is like this was the autocomplete results, right? You also see this when you are actually typing emails these days, either in Google. Sometimes you type something and then the rest of the sentence, it actually suggests you to complete the sentence. So this is one thing. Have you ever thought about like how this is done, or what is the mechanism behind this? Next one is spelling correction. So this is also another email I was trying to compose, and you see I made a spelling mistake by, like, I deliberately did this mistake, and it showed this like red underline below it saying that there is a mistake in spelling. And once I click on this, it shows some suggestions, right? So how this is done. So two examples that you all are familiar with, and something that you may want to know, like how this is done. So let's talk about a data structure that can really answer these two questions. So the data structure that we are talking about today is Trie Data Structure. Trie actually comes from this word retrieve. So this is the try part. And you will understand why this tries comes from retrieve just after a few slides of discussions, after a few slides of discussion. But for now, even if you don't remember this, this is trie is easy to remember because Trie data structure is also some kind of tree. Yeah, so there is similarity of pronunciation or similarity how tree and try sounds, but actually try comes from this word retrieve. So try, what kind of data structure is a trie data structure? It's a data structure that contains sets of strings. Okay, so in a trie data structure you will have different strings stored in it. You also can think like this is some kind of a dictionary. So a trie data structure contains different words, but how does it contain different set of strings or words? It saves it by character, okay, not it doesn't save the whole string together, it saves it character by character. Say here in these example, you see these words are actually stored in this trie data structure, but you don't see this whole word stored anywhere. You don't see and or and, right? You don't see it stored, or you don't see do. You say like, where is do? But this is how trie is different than a hash table or a dictionary. The words are actually stored character by character. So if you see, there is A, there is N, and there is D, right? So this makes up and then you have D, A, D. This makes up D, dad, right? So the thing is, every node, so as you see, trie is some kind of tree, but every node stores part of the keys instead of the key itself. So you see, none of the nodes has the whole word, right? It only has the part of the word. So every node has the part of the word, a character, and these characters together form words, right? So that's the simplest definition of a trie. It's a data structure that stores words or set of strings and it stores them by character, where each node stores characters. Each node, here is one thing, it doesn't necessarily store one character, it can store more than one character, but just each of those are actually known as characters. It doesn't store the whole word anywhere. Actually, it stores the whole word in the data structure itself, but inside one node, you won't see the whole word. Okay. Okay, so some properties of the trie. First of all, at the top of the trie data structure, there is a node, root node. Okay, so there is a root node in each trie. That's important thing. And then each node of a trie represents a string, and each edge represents a character. So you see each node how does each node represent a string? So let's say, what string does this node represent? Well, this node represents this string D A. Okay, you see that because from root till this node we have encountered D and A. So this node represents this string DA. What does this node represent? This node represents this string AN. Okay, because from root we have come to, we first find A and then it comes to N. Okay, and this node, say this node represents ANT. Okay, this is string. So each node, although it stores characters, but it can represent strings. And how to find that string? From the root, if you come all the way down to, the leaf, then you find a string that is represented by that node. And each of the edges represent a character. So you see this edge represents character A. This edge represents character D, right? So the edges or the links represent a character. We will actually learn more how that is achieved. Let's go ahead and we'll discuss that. So what does each node, a trie node? So you see we have node here, right? Each of these are nodes. What does each trie node contain? So first of all, it contains a hash map on array of pointers, each of which representing a character. And the second thing it contains is like a flag to indicate if the string ends at the current node. I think to better understand this, an example would be really helpful. So this is how, if I write in Java, this is, or Java or C#, this is how a trie node would look like. So this is any trie node. So say this node, it will have a value. Yeah, it can have a value, obviously. You see here for this node, the value is A. Not only that, it will have links to its children. We know about that when we were talking about binary tree. We knew that binary tree has two children, left and right. But what about a trie? A trie node, a binary tree node had like two children, but a trie node may have like many children. So this is the array of the children, right? This is the array of the children because it may have many children. And it will have a, as I say, like the second one, the flag, a flag which indicates if that node is an end of a word. So we'll learn about this thing as well. So this is the constructor. You see, for children, we are assigning like 26. This is for the ease of the discussion. We are assuming that all the words are made up of small cap letters, A, B, up to Z. Okay, so there are like 26 letters. So assuming that there are like maximum of 26 letters in my dictionary or string, all of them small caps, we are assuming for that, we are saying that each node has like 26 children, each of the children representing one small cap character. Okay, but if my string have can contain, say, other symbols and other things, in that case the number of children might be up to like more, 128 or 256. Okay, but for today's discussion we are assuming that all the strings that we want to store in this trie data structure are made up of small case characters. So we are saying like each node will have a value. Obviously it will have a value, and it may have like 26 children. Okay, and also a flag to say that if this is the end of the word or not. Okay, so let's see, let's take a look at this part, like these 26 children, how how it looks like. So this is a node. Say this node has a value, say this node. Okay, this node has a value. What is the value for this node? A, right? Okay, and then this has a flag, is word. Is word is false for now. And this is the list of the children, an array, right? So initially you see these, all of these are like null. Initially all of these are null, right? All of these are null, nothing is there. Okay, next you see that one of the children, like, is not null, so n. So one of the children, so we are actually focusing on these node. This can be for any node. So one of the children is not null. That means this one, all of these are nulls for now, but this one is not. So there is a, so what does it mean? It means that there is another node, right? Another trie node with n, and this one is linked to this. Okay, and this trie node will also have like a list of 26 children, and also it will also have this is word flag. Okay, so we have this for today's discussion. We are assuming that all the strings or words are going to be made up of small case characters. So this is how a trie node looks like programmatically. It will have a value, it will have a list or array of children, and it will have a flag. And this is how it looks. This is how it looks in a diagram, and this is how it originally looks like. Okay, so it will have a value, and then this is a list, array list of the children. And since we have like 26, so the 0th index will represent character A, and the last index will represent character Z. So this is the list of the children, and you see A has one child with value n. That means, what it means is this location has a reference to another node, another trie node, and it has only one children. Now let's look at, say, let's look at another node, right? So say, let's focus on this node, how this node looks like. Well, this node will have a value D, and you see it has two children, right? A and O. So these two are actually linked to two different trie nodes, right? And the others are like null, empty, because others are empty. Okay. Okay, so we'll show you further examples, and it will make these things more understandable. Okay, so each path from the root to any node represents a word or a string. So we already talked about this, right? So each path, say, so let's talk about this path, right? What does it represent? It represents a string, right? DA. Well, this is not a word. This is a string because the is word, we have color coded this. So the words are actually these deep green colors. These are words. And the others are like just strings. Or let's take another path, say this path, right? From root to this all the way. So it's A-N-T, A-N-T, and this is a word. You see the color code, right? So by the color code means these light green ones has is word false. And these ones have is word true. These deeper green ones, okay? Okay, so let's show you how we can insert words in a trie data structure. Okay, so forget about all of these lower part. Okay, say think that these are not existing yet, and this is a root node. Okay, so when you actually create a trie node, this is a trie node, right? The root node doesn't have any value, but it has the list of the children. So initially, you see like all of them are null. So initially, all of them are null, or let's make it white. So initially, all of them are null. When we actually created the root node, so all of them are null. Okay. So next, what we do is, you see, we want to store this word and into the root. And another thing is these parts are not existing. Okay. So we have only one node, the root node. And root node has this array of children, but it doesn't have any children yet. Now we are trying to store the first word, and. So and starts with character A, right? So we try to insert and into this trie. It starts with character A. So what we do is we create a node for A, and then we attach it as the children from the root. So you see, we have created a node A, right? We created this node A, and then we attached it to the first index, because 0 represents A for today's example, right? We attached it, and so far we have this. Next, we go to the second character, N. Okay, so when we actually created node A, do you see this? Like when we created the character node A, it has list of 26 children, and all of them are null, right? Okay, so now we come to the second character, which is N. So next, what we do is we create another node, another trie node, N, and we link it with the correct index, because N is a child of A, right? Okay, so whenever there is a something is turned into a real link, we are assume that we are changing the color to green. Everything white is still null. Okay, so we create N, and this trie node will also have the list of children, but though all of those are null yet, so I'm making them white. Okay, next we create the next character is D, right? So what we do is we create another node D, another trie node D. We link it with, and as you see, the it has the list of the children, but all of them are null yet, because we don't have any children for D yet. But D is the child of N, so we make this link alive, right? Okay. And finally, what we do here is not only that, we make, since this is the end of the word, so we make this end is word to true. For other nodes, it will like false. Okay, so there goes inserting and. Now let's try to insert ant. Okay, so how do I do that? First character is A. So I go to the root and see if already there is a child for at index 0, right? A represents index 0. Yes, there is a child. So I don't have to create a tree node again. I already have a tree node for A. So I go to the tree node A and now look for the second character N. And I check if the child for N, if already there is a child with N, we come to this index, whatever the index of N is, and we see that, well, it's not null. So we don't do anything. Already we have we have a child for N. So we go here. Next, we look for T. Okay, now we check for T. So we go all the way and see that there is no child for T yet, right? There is no child created for T yet. And this is null. So what we do is we create a child for T and then assign it as a child, create a node, assign it as a child. And this is the end of the word, right? So is word, we set the is word flag to true. Okay. So this is how we inserted two words and into a trie data structure. Okay, so initially we didn't have anything. We didn't have these node. We didn't have any of these node. Only thing we had is we had this root node. We had this root node with all the children empty, right? All the children were empty. This is initially what we had. That's it. And from there, we build different nodes to store these two words. Okay, so next we insert two other words, dad and do. So already our tree had this thing, right? And then we insert dad. So you see in the root node, so the root node actually look like this, right? So we don't have anything, D is still empty, right? So what we have to do is, if I want to create dad, what do I have to do? I have to create a node with D, right? That's exactly what we did here. We created a node with D from the root node. And similarly, we created, D didn't have any children with A didn't have any children with D. So we created this node and linked them up. So that goes into the tree. Next, we insert do. So we look for D here. You see already we have this, we had created this node. So we don't create it again. That's fine. But for O, we have to create this. So we create this. So this one was from before, but this one we created new and linked it. Okay. Okay, so what operations, once we insert that, what is the advantage of trie data structure? So one thing is we can search for prefix. Say someone asks you that, say I have my own dictionary where I have inserted different words, and someone asks you, does your trie have words starting with A N? an. Someone asks you, like, with the prefix of an, do you have words with prefix an? Yes. What you can do is you can start from the root node and see if there is a node for a. If that is the true, then if there is a node for n. If both of them are true, then you say, yes, true. I have words with prefix an. Okay. Or you can you can look for like whole words. So if the question is, does your trie have this word, has this word dad, not prefix, the whole word? So you start from the root node, you look for d, you have it. Then you look for a, you have it. Then you look for d, you have it. Not only that, you have to check if we say just is word, right? Is word is equals to true. If that is the case, then you can say, okay, yes, my trie already has this word. Okay, so you can search for it. Now, already some of you may have found that how these trie data structure can help in autocomplete and spelling. So let's look at one example. So this is an example of a trie. For now, ignore these numbers. Ignore these numbers. Okay, the numbers are there, but ignore the numbers. Just look at the other stuff. Okay, so here is the thing. In the previous example that I showed you, okay, let me show you so that it matches the previous examples. Assuming that although each node contains only one character, it represents a string, right? Okay, so someone is, say, Googling, right? And he types T. Now, say Google has this dictionary stored somewhere, right? As soon as you type T and then you type next, so you type T, that means already Google's internal trie is activated. It takes this path. So let's take another color. So it takes this path. Okay, so you are here already in Google's trie. Next, you type E. That means now inside the Google's trie, you have reached here. You are here. And now Google knows that from the trie data structure that it has stored, it sees that there the next steps might be this, or this, right? So it will already, so you are searching this, and in the autocomplete, it will start showing you the options. So if you come this way, potentially if you come this way, you will see this TEA, right? If you come this way, you will see TED. If you come this way, it's TEN, right? So it will start showing you these autocomplete results. You are here. So this is not the exact way Google does it, but this is the basic idea how they do it. If you are here, it already starts showing you results from the children because these are your potential destinations, right? So this is how autocomplete works. Or you type, say, IN. Say IN. So you start typing IN. And this one knows, okay, this is a so you are here. And already Google knows, okay, your potential destination might be this. So it will show you autocomplete with INN. Okay. So this is how, using trie data structure, we can implement autocomplete. Next, let's talk about the spelling. how spelling correction is made. Okay, so let's say you again started writing, say T, E, you are here, right? And then you wrote X or Z, something like that, Z. So you see that E, what are the children of E looking like? Let's try to look at the node here. So the node here has the value of E, and then it has a list of links, right? Or list of children. And you see this one, the first index is for A, the second index is for B, the third one is for C, the last one is for Z, right? And the something middle here is for N, this is for D, and this is for other ones. Okay, so you see from this example, these are empty, right? These are empty. A, D, and N is only there. So all these are empty or null. There is no children with these characters. So you try to write Z, right? So it comes here and checks and sees, oh, Z doesn't exist. So it's not a, probably this is a wrong spelling because the dictionary doesn't have it. So why don't I suggest the correct spelling? So it may start suggesting you. Since you tried Z, so it for T it successfully came here. For E, it successfully came here, and then for Z, it tried to come, and then it found that there is no child for Z. So that means either this word is not in the dictionary or you have made a spelling mistake. So what are the ones that are available? So you say A is available, D is available, N is available, right? So it will show you starting, say, 10, TED, or T, right? So these are the correct spellings that we will start showing you as suggestions. Okay, so this is also a very simplified version of if the dictionary, or say if you have a trie containing all the words, and how, so basically on the background, a search engine may have a large trie with all words in it, or and then once you start typing, it will just start traversing that trie and start showing you suggestions for autocomplete or for correction of spelling if there is a mistake happening. Okay, so this is now I hope you understand how trie helps in those two practical applications. Okay, so what is the time complexity of the trie operation? Well, you see it's pretty simple, right? So simple means when we are like looking for, say, dad, right? When we are looking for dad, we're going to root node and asking for, do you have a child with D? Well, it's just looking for, say, root node has a list of an array of child, right? And there is a position that is for D. So you can just directly go in here. So looking for D, you just can go in here and see if this is null or not. So say these are null, all of these are null. Say I'm crossing out the nulls, okay? But this one is not. That means, okay, I find D. Next, I go here. This one also has the list of the children, and there is one location for A, right? And this is not null. Others say some are null. So that means I found it here. So I come here. So you see, going to every node, what I do is I just check the corresponding location, right? I just check one thing. So if the length of the string is L, say, or N, if the length is n, so for each characters, we are going to one node and making one search in the children list. So that means the searching will be just order of n, right? Similarly, for the insertion, when you are actually inserting into that trie, right? We are doing the same thing. When we are actually inserting ant, we're just going here and checking, oh, okay, if there is already a child for A, if there is not, I am creating one. If there is one, then I'm just going to the child. That's it. So I'm just going to the index. Next time I check for n, I just come here and check for n, right? Next I go for t, I just come here and look for t, right? So that means for each character, I'm just going to one node and just looking in the children list. That's it. So that means if the length of the string is n, then I need to do just n operations to insert it. Okay. So this part, like deletion, this is something that I would leave as a home task. Just search Google, like deletion from a trie, and you will find it. Go to Geeks for Geeks. They have a nice explanation for the deletion. Okay. And once we're inserting, you see that if you are inserting m words and each of them have like length of n, so basically we are creating nodes, right? So in total, we will be creating order of n into m nodes. This is the worst case. Like sometimes we will be creating less. Say when we are actually inserting and then ant, we didn't create like 6 nodes. Instead, you see there are some common nodes, right? an was common in both of them, so we created 4. But in the worst case, we had to create like 6 nodes, ant and and. So that means once we are inserting, if they're like we are inserting m words, and then if you are inserting m words, then and each of them are like of length n, then in total, in the worst case, we have to create n into m new nodes. And for searching and deletion, we are not creating anything, so we don't need any extra space. Now, one question, obvious question that you may ask, like, okay, so if you want to store words and strings and create a dictionary, why don't we use hash map, right? So we could just simply create a hash map and put, say, uh, this is a, say, hash map, and then we could put our words and, right? And then we could put, say, ant, we could put do, dad, right? We could just put the words, and next time we could just, if someone says, okay, hey, does your dictionary has dad? We could just go in here. But one thing here, remember one thing, like once we insert dad into the hash map, it wasn't going to the hash map directly. You remember the hash function, right? So there was a hash function applied on, say, dad. That hash function gave me a value, say for this one, say index 4, right? So this one was giving me index 4, and then I was going to index 4 and putting dad there. That is one thing. Okay. And obviously, hash maps have other issues, like there might be multiple strings and words going to the same place, but just still let's assume that this was a very good hash map and every word was mapped to different location. In any case, so if someone says like search this word dad, it would have used the same hash function, got the same result, and searched here and says, oh, okay, dad is already there. But if we could use hash map then to store words or make a dictionary, why do we want to use trie? Okay, so here is a few things. Say we insert another word, say dash. Okay. Now, we showed you one example. We can use prefix search. So someone says, hey, does your dictionary have words starting with DA? Now you are in problem because you cannot just apply hash function on DA, right? In that case, DA is going to is not necessarily taking you here. So putting hash function on DA is not necessarily taking you here or here. It may take you somewhere else. It may take you here, right? Because this is a different word. So prefix search is not working. So if someone says, hey, does your dictionary has this DA, like DA words starting with DA, what you have to do is you have to check the whole hash map and look for words and see if that word starts with DA, right? But with a trie, it was very simple. You see, we just was starting from the root node. If someone looks for DA, well, it says, oh, I don't have any child with D, so false, right? I don't have to look at everything. Or if I really had a node with DAD, I could just come here and then come here and say, oh, okay, I already found DA, so true, yes. So that's one example, advantage of trie on hash map. We can efficiently do prefix search. Not only that, we can easily print all words in alphabetically order. So this is another one. You see in a trie, it's like all, if you print a trie, it will be in an alphabetically order, right? If you print this, you see and dad, do, right? If you go from left to right, is you can print all of them in alphabetic order. But in a hash map, you don't know which one is where. You see and is here, do is here, ant is here. You cannot print them alphabetically. And obviously, these hash function, we can avoid this. In trie, we don't need to do that. We just go to the root and check for the children. So we can, there is no, these, whatever overhead is due to this hash function, we can avoid that. And the final thing is, even for a string with large collection, so say my hash map is not that big. Say my hash map has, say, how many locations? For this hash map, it has 6, okay? But I have put like 100 words into this hash map. That means each of these locations will have like 10, 15 words, right? So someone says, okay, look for a word, apple. What I do is I apply hash function on it, and I find, say, value as 5. I go to index 5, and even still now, if I want to find apple, I have to look through this whole list, right? Suppose I have to check another 9 words to find apple. Just talking about a hash map that is not big enough, where each location has multiple words. But if you are putting in a trie, whatever it is, like, look at this trie, right? Whatever it is, like how many words you put, all you need to do is you have to go through all just one path, just number of characters, right? So any kind of search is done in order of n, where n is the number of characters in the string. And obviously, the number of characters, we expect them to be, in a word, we expect the number of characters to be not long, right? Constant, even if it's like 50 characters. You can think it's almost in constant time. So this is another advantage of trie. So overall, that's it about the trie data structure. So we talked about the trie data structure, how to insert into it, how a trie node looks like, how to insert into it, how to search for a string or a prefix in a trie data structure. And then we talked about like what is the advantage of trie data structure over hash map. And we talked about two applications of trie data structure. One is autocomplete and the other one is a spelling check. So that's it for today.